I am Wim Leemans. I'm director of the Accelerator division here at DAISY. Before that, I was 27 years in the USA, Lawrence Berkeley National Laboratory, where I carried out a career in research on compact accelerators, laser plasma accelerators. So I was a graduate student at the University of California, Los Angeles. I was on the 4th floor in a building called Knudsen Hall. And we were actually building a laser system with some detectors, and we were playing the radio as entertainment. And all of a sudden the radio flash came on, the Berlin Wall has fallen. And it really, it sent sort of a total consternation amongst all the people in the laboratory. Everybody became quiet and we all listened to the radio. So it's really an unforgettable moment. So as a child, I always wanted to go into engineering. I loved airplanes, and when I was in second or third grade, I actually asked my father, why am I wasting my time in elementary school? Couldn't I go immediately to a school where I learn how to build airplanes? So now I'm not building airplanes, I'm building accelerators. But this was something that I already then knew I wanted to build things. I think parts of myself, of who I am, loves to invent and come up with new ideas that could really have an impact on society. So I feel part inventor, certainly experimentalist, explorer, I would say. The wall that we are working on breaking down this wall would enable us to build accelerators that are far more compact than the ones that we're used to today. Here I'm holding in my hand an example of an accelerator that we used. This was from my time at Berkeley. It's a 9-centimeter accelerator that enabled us to achieve an energy of an electron beam of over 4 billion electron volts. And to put that into scale, with a conventional accelerator, you would need roughly something on the order of a kilometer of a machine. This is then enabling us to make accelerators where the accelerator can go to the problem. One of the key things that we achieved over the years of research, the original idea came out about 40 years ago. Of a concept where the technology at the time was not ready for implementation of this concept. Over the years, over the decades, this concept became more and more mature. Why? Because laser technology became better and better. Just in 2018, the Nobel Prize was awarded for the invention of a laser technology. That is a laser technology that we use to drive our accelerators. They rely on a laser pulse getting shot into a plasma, exciting a wave, and electrons essentially surf on that wave to reach very high energies. So once you have accelerators that are compact, you can think about all of the applications that enables. Accelerators are used in medicine, in industry, inspection tools, etc. But usually those devices are too big to be mobile. So by making them small and making them mobile, you could imagine having an accelerator go to a hospital in a rural environment to do either imaging of cancerous tumors in the body or even potentially treatment of these cancerous tumors. And so this is for me very exciting, that we go from something that was conceived many years ago already, worked on it for decades, and that eventually now it's leading to near-term applications of this technology that with conventional accelerators we simply couldn't have implemented. So I think right now, because of all the progress that we've made, I sleep better and better. I must say. I think the key things that we need to demonstrate are that these electron beams can be of the quality similar to the conventional accelerators. We want to show that the electron beams produced by the laser plasma accelerator are capable of driving a free electron laser. So that's something that is near term. And then the second element that we're working on is making the repetition rate, the number of pulses per second, higher and higher, so that we can drive the applications where you need lots of pulses per second.